I have another gradient quiz. Consider the following quadratic error function. We are considering the gradient at 3 different places, A, B, and C. And I ask you which of the gradient is the largest. A, B, or C, or are they all equal? In which case you would want to check the last box over here. And the answer is C. The derivative of a quadratic function is a linear function, which will look about like this. And as we go outside, our gradient becomes larger and larger. This is over here much steeper than this curve over here. Here's a final gradient descent quiz. Suppose we have a loss function like this, and our gradient descent starts over here. Will it likely reach the global minimum? Yes or no? Please check one of those boxes. And the answer is yes. Although, technically speaking, to reach the absolute global minimum, we need the learning rates to become smaller and smaller over time. If they stay constant, there's a chance this thing might bounce around between 2 points in the end and never reach the global minimum. But assuming that we implement gradient descent correctly, we will finally reach the global minimum. Now, that's not the case if we start over here, where we can get stuck over here and settle for the minimum over here, which is a local minimum and not the best solution to optimization problem. So one of the important points to take away from this is gradient descent is fairly universally applicable to more complicated problems, problems that don't have a closed form solution, but you have to check whether there's many local minima, and if so, you have to worry about this. Any optimization book can tell you tricks how to overcome this. I won't go into any more depth here in this class. It's interesting to see how to minimize our loss function using gradient descent. In a linear case, we have L equals sum over the correct labels minus our linear function to the square, which we seek to minimize. Now we already know that this has a closed form solution, but just for the fun of it, let's look at gradient descent. The gradient of L with respect to W1 is minus 2 sum of all j of the difference as before, but without the square, times xj. The gradient with respect to W0 is very similar. So in gradient descent, we start with W1, 0 and W0, 0, where the upper cap 0 corresponds to the iteration index of gradient descent. And then we iterate. In the mth iteration, we get our new estimate by using the old estimate minus a learning rate of this gradient over here taken at the position of the old estimate, W1 m minus 1. Similarly, for W0, we get this expression over here. And these expressions look nasty, but what it really means is we subtract an expression like this every time we do gradient descent from W1, an expression like this every time we do gradient descent from W0, which is easy to implement, and that implements gradient descent. Now, there's many different ways to apply linear functions in machine learning. We so far studied linear functions for regression, but linear functions are also used for classification, and specifically for an algorithm called the Perceptron algorithm. This algorithm happens to be a very early model of a neuron, as in the neurons we have in our brains, and it was invented in the 1940s. Suppose we're given a data set of positive samples and negative samples. A linear separator is a linear equation that separates positive from negative examples. Obviously, not all data sets possess a linear separator, but some do, and for those we can define the algorithm of the perceptron, and it actually converges. To define a linear separator, let's start with our linear equation as before. w1x plus w0. In cases where x is higher dimensional, this might actually be a vector. Never mind. If this is larger or equal to 0, then we call our class label 1. Otherwise, we call it 0. So here's our linear separation classification function, where this is our common linear function. Now, as I said, perceptron only converges if the data is linear separable, and then it converges to a linear separation of the data, which is quite amazing. Perceptron is an iterative algorithm that is not dissimilar from gradient descent. In fact, the update rule echoes that of gradient descent, and here's how it goes. We start with a random guess for W1 and W0, which may correspond to a random separation line that usually is inaccurate. And then the mth weight I is obtained by using the old weight plus some learning weight alpha times the difference between the desired target label and the target labeled produced by our function at the point n-1. Now this is an online learning rule, which is we don't process all the data in batch. We process one data at a time, and we might go through the data many times, hence the J over here. But every time we do this, we apply this rule over here. What this rule gives us is a method to adapt our weights in proportion to the error. If the prediction of our function f equals our target label, then the error is 0 and no update occurs. If there is a difference, however, we update in a way so as to minimize the error. Alpha is a small learning weight. And once again, perceptron converges to a correct linear separator if such a linear separator exists. Now, the case of linear separation has recently received a lot of attention in machine learning. If you look at the picture over here, you'll find there's many different linear separators. There's one over here, there's one over here, and there's one over here. One of the questions that has recently been researched extensively is which one to prefer. Is it A, B, or C? And even though you probably have never seen this literature, I want to just ask your intuition in this following quiz. Which linear separator would you prefer if you look at those three different linear separators? A, B, C, or none of them?